So it's my pleasure today to welcome Quan Vuong for our guest lecture. He co-founded Physical Intelligence and focuses on large-scale pre-training for cross-embodiment robot models. He obtained his PhD at UCST, during which he was advised by Henrik Christensen and Hao Su. And before co-founding Physical Intelligence, Quan worked at Google DeepMind, where he started and co-led RTX and OpenX embodiment projects. And with this, please give him a warm applause. Go ahead, Quan.
Sounds good. Yeah, I mean, I can actually see the Zoom link, and I'm not going to try to make it show up. So, if you have anything, feel free to interrupt me. So I'll keep today really informal, just to share what our recent progress is. And I think my goal today is really to interact with the robotic community at ETH. So if you have any questions, save them for the end. So π0.7, this is a work that we released recently. And I would say that one of the main innovation in this work is to get a single model that can perform many tasks and perform many tasks at an extremely high level of performance. Why is this important and why is this hard? So first, why is this important? Previously, when you wanted to get really high performance for any particular task in end-to-end learning, normally what you do is you take a pre-trained model that are somewhat reasonable in performance, not great, and then you post-train that model to that specific task. And the reason why getting a single model that can perform many tasks at high level performance is important is that it's much more scalable, right? You now don't need to worry about which model checkpoint, what is hyperparameter during test time I use for a particular task. The fewer model that you have to manage, the easier it is for you to scale. And it's hard because it's just not obvious how to do it. It's a really open research question, and π0.7 by no means solved this question of how do we get the best model that can perform many tasks, but I think it's a meaningful improvement. And so I think we're in the age of scaling for robotics, and when people talk about scaling, usually there are two main axes. There's data and there's model, and one challenge is that it's just not obvious what do you scale and then how do you scale it. For example, if you take all of the data that you might have in robotics and you train a model on it, most likely it won't be a great model. It won't be as good as a specialist model that has been really heavily tuned and optimized for a particular scenario. And if you look at face value, what that means is more data doesn't equal a more performant model. So the majority of the rest of the talk will focus on how π0.7 was able to produce a single checkpoint that can match specialist performance. So if you look at the top right of this slide here, what this is showing is a figure from one of our previous work called RL token. X-axis is the episode length of episodes seen during evaluation, and Y-axis are success rates. What this is illustrating is that the green are demonstrating the speed of a human teleoperator controlling the robot. The slightly pink, the base policy, is illustrating the speed of a policy trained on the teleoperation data, which is actually slower than the speed of the human teleoperator, which is kind of interesting, right? Because you would expect that good imitation learned policy will at least reproduce the speed that you see in your training data. And then the yellow, which RL token wanted to show, was that if you perform online reinforcement learning, you can get the speed to be superhuman in this case, where you can see that the yellow plots are to the left of the green plots. So one reasonable question that you can ask here is, first, how is it possible that you have a data set, you take a policy, you train on that data set, and the policy is actually slower than the data set? And how is it that, how do you get a generalist policy that have the same speed as the specialists that were trained using online reinforcement learning? So here comes π0.7. π0.7, in terms of the architecture of the actual action generation component of the system, has not changed significantly from our prior work. It's very similar to π0.6, very similar to π0.5. We use a language model and a pre-trained vision encoder and then we kind of graph an action expert onto it to teach the model on how to speak robot language, if you will. So the model takes in a prompt, for example, clean the kitchen. It might also additionally take in a subtask prompt, which indicates a subtask that if you do it and if you finish, the rest of the subtask, you will finish the task instruction. And additionally, there are metadata that indicates the speed and the quality of the episode that you're training on. One other innovation in π0.7 is the goal condition capability of the model that leads to much better generalization that I'll also touch on later. Oops, I can't go back to that. Here we are. And so what I just talked about are the action generation component of the system. There is also a high-level component, and the way to think about the high-level component is it's sort of like a planner. It's the high-level which are indicated either by the human or the high-level policy or the world model here are not capable of generating low-level actions themselves, but they are capable of generating plans for the low level to figure out what action to take to execute on those plans. So to show you the kind of tasks that the π0.7 model are capable of, and these are tasks that stress test very different axes. There is laundry folding, which has to deal with infinite state space. There is really precise tasks of screwing a tiny screw into a robot arm on the right. There is a task of building a box that require really precise two-hand coordinations. And there's a long horizon task of taking out the trash on the bottom. And the noteworthy thing here is that all of this video and all of these tasks were performed by a single checkpoint from the π0.7 pre-training run. These are kind of figures that I won't go into the detail, but the main takeaway here is first, let's look at the different policies that are presented here. So there is π0.7, which is the pre-trained model, and there is what we call RL specialists and SFT specialists. And to abstract away the detail, the way to think about these specialists is that these were policies that were specifically tuned to get high performance on specific tasks. And if you glance at the slide, you can kind of see that the yellow, which is π0.7, is either the same or actually better than the specialist, which is the point that I was trying to get across, which is I think this is the first time where, at least for Pi, it's possible for us to get a single checkpoint that perform as well as policy that are specifically tuned for different tasks. Now, the even more interesting bits here is that in some of these plots, you see that the yellow is actually better than the specialist, which is interesting, right? This is saying that when you have a specialist that has been specifically tuned for a particular scenario that are already very high performing, now, if you can get a generalist to also perform well in those scenarios, the generalist can actually perform better. And now, why is that the case? That is the case because in large-scale robotic evaluation, really every evaluation is a generalization evaluation, where you try to have control experiments and you try to fix the scene as much as possible, but there's always going to be some factor that change. And because you have a generalist, it's going to be generally more robust to subtle change in the environment, and therefore can actually outperform the specialist. And we really try our best to make it an apple-to-apple comparison here in terms of data that different models are allowed to see. Now, one of the interesting plots from the π0.7 paper is this plot on the left here. The x-axis is the percentage of data used in training, where as you go towards the left of the x-axis, you use fewer data, but the data are higher quality. And if you go to the right axis, to the right of the x-axis, you use more data, but the data are lower quality. So when you go across the x-axis to the right, you are increasing the volume of data that you train on by adding lower quality data. And there are two policies that are being compared. There is π0.7 without metadata. And we can see here that increasing the data volume actually leads to decreased performance when you go from 80% to 100% when you add the really low quality data into training, which is a kind of experimental evidence that illustrates the point that I made at the beginning, which is that more data is not necessarily better. Now, the other interesting bit here is that the second policy that are being shown, π0.7 with metadata, there is a huge jump in performance going from 80% to 100%. And this is by adding lower quality data. And so this is showing a plot where by representing information to your policy properly, you can actually benefit from lower quality data and benefit in a pretty dramatic way. Now, in addition to all of the things that I just mentioned about high-performing policies, one other really interesting result from π0.7 is cross-embodiment transfer. Now, how do we categorize cross-embodiment transfer here? Let's say you have these two robot arms here. You've collected data for folding a shirt, and this is a task that's hard. This is a task that can require up to like hundreds and hundreds of hours of data, because it's a pretty precise manipulation task that also has to deal with a very large observation space. Now, with π0.7, it's possible for you to take the policy checkpoint that was trained on only short folding data from the robot on the left, and now run it on the robot on the right here, which is a station of 2 UR5, and have the station of the 2 UR5 performing short folding as well. And we've never included any short folding data at all from the biome UR5 station. So this is generalization to an unseen task on a unseen robot and task combination. And one other thing that's interesting to me about this result is that this is not a simple task. This is a very difficult task, and we were very surprised how well the policy works in this case. Thus far, I haven't touched on the high-level planning aspect of π0.7. What this video are showing is that if you have a human that's coaching the robot by giving language instruction, you can actually get the system to perform tasks that you haven't collected data in before, and also on completely unseen environment, unseen objects. Like this is the task where the human is trying to coach the robot to air fry a sweet potato, and the air fryer are just not in the training data at all. Let me skip this slide. So At Pi, we believe that robotics is very far from being solved, and we really want to help propel the community forward whenever we can. And part of that effort is to create the infrastructure for everyone across the world to experiment with robotics. So we open source Pi0 and Pi05, and people are always very surprised when they ask me the question, is there any difference between the Pi0 and Pi05 model that is open source and the model that researcher uses at Pi? And actually there is no difference. The checkpoint that we open source for Pi0 and Pi05 are also the checkpoint that researcher at Pi uses for the daily work. One other thing that I wanted to show, which isn't on the slide, is this blog post that we did called the physical intelligence layer. I'm showing the blog post here with the URL so that you can look it up yourself later on as well. The reason why this blog post is interesting is you can ask the question, if Pi can build a really great robotic model, and when Pi does so, how does Pi externalize it? That is to say, how does Pi make that intelligence available for the rest of the world to use? And as part of an exercise to understand how Pi make that model available for the rest of the world to use, we work very closely with robotic companies that want to deploy robots today to see if the model and the system that we're building and they're also building are good enough for real tasks today. And the first video that, the first video that you see when you go to this blog post is a video of a robot from Weave Robotics that are folding laundry in a drill laundromat in the Mission, which is where in San Francisco that Pi and Weave are in. And this is interesting. One reason is because they are completely unseen clothing items, and this is performing laundry folding for a real customer order. In the blog post, there are also examples of various scenarios where the robot has to be somewhat intelligent to recover from either error or to be able to fold a really complex item of clothing. For example, these jeans with really long pants. It's pretty hard to fold because the two legs of the pen would get tangled together. So that's one example. The other example that the blog post show is this example of a robot packaging a task. Now what the task here is, well, I'm not sure how it works in where you guys are, but in the US, if you order an item from Amazon, it sometimes comes in this small soft pouch that the package in. And the task here is that there is a tray containing various kind of items, and the robot is supposed to pick them and put it through this really small gap here into the packaging machine. And then when the package is sealed, the robot is supposed to pick up the package and put it over here to be ready to be shipped out. And this task is hard because one of the diversity of items, like there can be many different kind of items that the robot is packing. The second reason why it's hard is because this is not a task that's easily automatable using a classical stack, because errors can happen. The pouch itself is a small deformable object. One of the things that I really love about this video is this is daytime, right? This is when in the morning when the robot is running, and if you scroll to the end of the video, you can see that it's nighttime. So this is a robotic system that's performing a real task, packaging real customer order in a real warehouse, and it's running a full day workload. And the majority of it are autonomous. So I think this example was pretty extraordinary to me because it didn't even require that much data to get this level of autonomy. And so the takeaway here is we want to figure out how do we externalize the intelligence, the model that we're building. And one way to do so is to work with companies that want to deploy robots today and scale the deployment and to work really closely with them. We work as if we're on the same team. It's very free flow of information to see if the system that we built together with this company are good enough for deployment. And one of the really critical aspects in this deployment are the ability to make mistakes and to remotely intervene when the system makes a mistake so that the system can recover. And one of the key questions is, can you get to a level of autonomy where you don't need to remotely intervene as much and you're essentially break even from a financial perspective so that you can scale deployment. And I think, for some of the tasks that we work on with partner company, we are essentially there. So with that, let me end the presentation. I want to leave some time for questions and answer and discussion. Feel free to ask me anything that's on your mind. And if you want to learn more about us, please go to our website, pi.website, and take a look at our blog posts. We put a lot of effort into making them presentable. Thanks for listening.
Hey, so Sergey said that you can get quite far with like a gripper hand, but since you're now incorporating data from humans, is it maybe now time to get like a more dexterous robot? Yeah, so the problem with, I think what you're referring to multi-finger hand is the following. It really depends on whether you want to build hardware or you want to study intelligence today. Because if you want to study intelligence today, then you would like to have scale. Or we believe that scale is important for intelligence behavior to emerge. Now, what do you need to scale? In terms of hardware, you need hardware that is cheap, that is reliable, and that is easy to tele out. And if you look at multi-finger hands, you can get 2 out of 3 today and not all 3. Like you can get a hand that is reliable and easy to tele out, but it's not going to be cheap. Like, for the price of one multi-finger hand, you can get maybe 6, 7 robotic system with 2-finger grouper. Or you can get a multi-finger hand that is cheap and easy to tele out, but it's not going to be reliable. Like it would break so often that you would wonder, why am I doing this in the first place? Yeah, and so that's one argument why if you want to focus on the intelligence question, studying that using multi-finger hands is a little bit of a distraction today. Now, this is not to say that multi-finger hand is not important. I think it is. And when the hardware gets to the point where it satisfies those 3 criteria, then we'll consider working on it. And the other thing is, we probably work on like thousands and thousands of tasks at time at this point, and we work on really realistic tasks. And we haven't seen that many tasks where you actually need something more than a 2-finger mechanism.
Okay. First, nice presentation. I just wanted to ask about the scaling of these VLA models. Right now, I see that in your paper, you are getting some good cross-embodiment generalization results, and the hardware is reaching a point where it's actually very cheap. So what is stopping you from building like big data generation farms with thousands of people like collecting multitask data and then training the model that you can just deploy in any home? Do you have like very obvious bottlenecks that you are trying to solve at this point, or you think that we reached this point actually?
I see. Great question. So let me tackle the last thing in your question first, which is deployment of robot into the homes. Now, I want to build a home robot at some point, but I think it's just incredibly hard to do and may not be the right thing to do today. Because I think robots in the home, in the limit, is kind of like a physical AI complete test. Like I think if that works, then we would have solved physical intelligence. And so that's the
like science answer, there is also a economics answer where consumer robotics is just really hard, and selling into the home in a way that, like creating a product that's compelling, that is cheap, that is safe, it's just really hard. And because we believe that robotics today are bottlenecked by model capability, we want to focus on the research question first. Right, so why not the home today? That's the first part. And then the earlier part about your question, why not collect lots of data and have data collection farm? We're scaling data collections. You know, there are many other companies in the world that are scaling up robot data collection. The critical question is really, what do you scale? Because there are many axes. For example, do you collect data on many different tasks and only a little bit of data per task? Do you collect data on not so many tasks, but lots of data per task? What about human video? Do you collect lots of it too? What about Yumi? What about the robot embodiment? Do you collect data on lots of robots and not as much data per robot? Or do you collect data with only a few robot platforms with lots of data per platform? How do you change out the objects? In what environment do you collect the data from? I don't think these questions have an answer today, and they really need to be experimentally validated as to what's useful. And so, you know, we want to be good scientists, and we'll study how to scale by running experiments.
Hi, thanks for the great presentation. I wanted to ask regarding the difference between π0.6 and 0.7. So for 0.6 in the paper, you talk a lot about the problem with interventions during training and like how much human feedback you need. And you also very clearly today highlighted like some of the benefits of 0.7, you know, outperforming some of the specialized tasks and all of that stuff. But I wonder, like, with regards to training, how much were you able to reduce the interventions, and how much more efficient is it to train 0.7? Like beyond the performance benefits you showed.
Yeah. Are you referring to the intervention during data collection or evaluation?
Evaluation.
Yeah. I don't remember the number off the top of my head. The number should be in the paper. And we generally measure throughput of the overall systems. There should be some intervention number in there as well. My kind of general summary of the result is that there are just tasks that π0.7 can perform at a high level of performance that π0.6 just can't do at all. For example, this screwing a very tiny screw in the robot arms. π0.6 just really can't do the task at all, unless you run specialist post-training for π0.6. And there was a figure that I shown where the π0.7 model is actually outperforming the π0.6 specialist, especially in terms of throughput, because the model is more robust to environment change. And so it generalized better, like maybe the lightning has changed, or the object has changed, or the station itself has changed. So that's in terms of intervention during evaluation. Now, you also mentioned the question of training efficiency. There's multiple ways to define training efficiency. One of the one that I think a lot about is how much compute going to the training run. I would say between π0.6 and π0.7, they are roughly comparable actually, which is great because you get a much more performant model while not having to increase the scale of your compute significantly. I'm not sure that answered your question exactly. Happy to answer follow-up.
Yes, that was great.
Thanks a lot.
We have one more question?
Yeah, thanks a lot for your presentation. I just saw that π0.7 has a small word model for goal conditioning, and I think directly I'm thinking about Dream Zero as a full word action model, and so I'm guessing what are the differences, trades of, I guess it's not black and white, so are you leaning on towards more word action model maybe in the future, or because of inference costs, training costs, and data collection, it's not needed? And also, have you reached a fundamental bottleneck with VLAs that would be solved with word models, or maybe you think that fundamentally there's not a difference between the different models?
Yeah, that's a good question. I don't think there is a definitive answer to your question today. Like, I think all of the things that you asked are still open research questions. We're exploring some of it, the community exploring some of it. I think really what's crucial when I think about this question is one, model capability. For example, you want long context length. You want a model that's steerable. You want a model that is high capacity enough to ingest really large data set. And I think VOAs or video model can do both, but the way that you train them might be quite different. So one is, model capability. Number two is inference time constraint, as you mentioned. And the reason why I mentioned inference time constraint here is I actually think it's a very solvable problem. Like, if we get to the point where you have a really large model that is intelligent enough to perform tasks at a very high performance level, and then the only remaining obstacle is to make the model inference faster, I think that's a very solvable problem. And so it would be great if we get to that point. Now, we need to scale up the model, right? Like, currently the model is single-digit billions. I have no doubts this year we and the community will have low double-digit billions, and then it's going to go to mid-range billion, double-digit billion, then it'll go to high-range double-digit billions. And so the model size will continue to increase. And I think we'll see much more interesting emergent capability when the model size increase. Whether that's a VOA or a video action model that will scale better, like, we need to try to scale both up. Like, I don't think I have seen enough result in the community to say that one is obviously the better choice compared to the other.
Thanks. Do you have time for one last question, Quan?
Yeah, go for it.
Hey, thanks for coming here and giving the talk. I was wondering if you could elaborate on what you said before on why you don't want to do a home robot right now. Because in your public demos, sometimes you do go to homes and collect data in homes and show that you can do some home tasks to some reasonable success rate, and I think even generalized to new kitchens sometimes. So is it that you don't think if you get a reasonable, non-100% success rate on home tasks that consumers won't buy it? Or is it that you're concerned about safety and that you would want to wait until you have a really good model to make sure it doesn't break things or hurt people? Or why would you not focus on home robots? Because in my mind, I would think that consumers would tolerate a 60% success rate in a robot, loading a dishwasher and folding your laundry, because it's so useful and it's fun, and there's no economic output tied to it as it would be in commercial settings.
Yeah, so I think the dream of home robot is very real. I would like very much to build a home robot at some point too. Now, there's a few things in your question. The first things is Pi show a lot of demo on home tasks. Why is that the case? When we released Pi 0, I think the community thought of us as a laundry company because so many of the tasks were laundry-related tasks. Now, we pick home tasks for a very specific reason, is that it's a really good test bed for research and communicating that research. It's a good test bed for research because the full complexity of dealing with open-ended environments are there. It's a good set of tasks for communicating the research because one, the tasks are very relatable. We know robotics, but if I were to show a very precise assembly task to the layperson in the world, they're not going to be able to really grasp how interesting or how impressive it is. Whereas if they see a laundry folding robot, they kind of get a sense that it's hard and that this would be useful to them eventually, right? So communication of the progress to the layperson. We can look at an assembly task and understand that it's hard because we know robotics, but that's not the case for the layperson. And regarding why not go for home robot immediately right now, I think the model are not good enough. You might be okay with a 60% success rate dishwasher robot, but someone else might not be, or someone else might care a lot more about human-robot interactions, or someone else might care a lot about the robot should not take up too much space because they don't want it to get in their way. So I think diversity in human preference is one of the reasons why consumer robotic is really hard. And we think the bottleneck actually to build a really good home robot eventually is model capability, and we want to focus on that bottleneck first. I don't think if you take the model today and you try to build a home robot with it, you would be very successful. I think that multiple scientific breakthroughs should need to happen for that to be true. Now, the strategy that we take is very explicitly general purpose robotics, right? And you can think about how in language model, you don't have to solve language before the model are useful. And so we want to be at a position where our surface area for success is really large. And in some of the tasks and some of the environment, model are good enough today for deployment. And we want to go after them while still building up model capability so that the surface areas for success is larger and it's increasing. And eventually, home robots will be one of the things that the model are good enough for.
Okay, thanks.
All right. I think that's the end for Quan. Let's thank him again, please, for an amazing talk.